So now let us discuss preparation of phenol. There are about 6 different methods given for preparing phenol. The first one, which is also an industrial process, and it is also called the Dow's process. This is a process which is normally used on a commercial scale for preparing phenol. The starting material is chlorobenzene, and chlorobenzene is subjected to some extreme conditions. It is treated with 6 to 8% aqueous NaOH, and the temperature needed is about 623 kelvins, and the pressure used is about 320 atm. This can also vary to about 300 atms. So that's all right, and this would give us the first product, which is a sodium phenoxide. Also, so I may write this is chlorobenzene, this is sodium phenoxide, and this sodium phenoxide further gets acidified to form, so it's like H plus and or dilute HCl you can write down directly. So that's, I think, dilute HCl, and it can give you phenol. So this is the first method of, or first synthetic route of producing phenol, also a commercial process, and known by Dow's process, by the name of Dow's process. Okay, so what kind of reaction do you think is this? What kind of reaction do you think is this, and how should such a reaction proceed? One of the things that you observe here is that the reaction here is called SNAR type of reaction. This reaction is called substitution, nucleophilic, aromatic. And if you want to know how this reaction actually proceeds, a simple understanding could be, or a simple way to show the mechanism could be, you may take up chlorobenzene, and here there is this nucleophile OH. Generally, if you consider why, see here basically OH is replacing Cl. So why would OH replace Cl? For one simple reason, as a leaving group, so chlorine Cl minus is a better leaving group as compared to OH minus. How do you think you can understand the leaving capacity of any group? A simple understanding once again is that capacity of any group to leave in SN reaction, this is inversely proportional to its basicity. So here we find that stronger base would be a weaker leaving group. That's how it is. Now, what would be the first step? The first step would be OH attacking this carbon the electrons moving here. This is Cl, this is OH, and now you have your lone pair getting conjugated, and so lone pair becomes a pi bond becomes a lone pair, and you have, you know, this continuously happening. We can have more such forms, so I'm just writing etc. And now what would be the next step? So the actual stabilization of the structure comes from resonance, and what would be now the next step of how the product gets formed? Let us make this, put this aside first of all. I don't need it. Oh, now you just put this, that from here you may also have, or I may draw this once again, and I may write the step which leads to product formation is this. Ring restores its aromaticity, and we have OH and Cl minus. So this is how, this is an approximate mechanism that you can put forward just to show why would OH replace chlorine. Remember one thing, in such SNAR reactions, any electron withdrawing group in ortho or para position to leaving group, any electron withdrawing group in ortho or para positions to the leaving group will increase the rate of such reactions. Remember this. So by putting some electron withdrawing groups here, you can always increase the rate of such reactions. So this was the first process. We have phenol produced by Dow's process. Now we take up the second method for producing phenols. The second method of producing phenol is from benzene sulphonic acid. You have to know that benzene when treated with oleum, oleum is nothing but H2S2O7, also given as H2SO4 plus SO3. Benzene treated with oleum can give us benzene sulphonic acid. Benzene sulphonic acid. Now here, this SO3H group is a kind of reasonably good leaving group, a better leaving group as compared to OH. So when this benzene sulphonic acid, once again you have a good leaving group here, and so when you heat this or fuse, this is solid, so when you fuse this with NaOH, solid NaOH, right, and the temperature needed is about 623 kelvins, so this is solid fusion, you may end up in getting a substituted product, which is like O minus Na plus sodium phenoxide. This is sodium phenoxide, and this sodium phenoxide, you have about 2 molecules of NaOH used up, and so the other product that you get is Na2SO3, and you also have 1 mole of water separated. This sodium phenoxide which you get is acidified with dilute HCl, our standard reaction, and it would give us phenol. So this is again one more way of producing phenol. Here once again we use a good leaving group and get an SO3H here is our leaving group. It leaves and OH replaces it. This is also a kind of SNAR reaction in which OH replaces SO3H group. Okay, now let us start with the next method of producing phenol. Here we start with a primary aromatic amine, something like aniline here, and we first of all perform its diazotization. Now diazotization is a reaction which is done by reacting a primary amine, a primary aromatic amine, with a mixture of NaNO2 and HCl, which actually is nitrous acid, HNO2. So HNO2 is actually the outcome of NaNO2 being mixed with HCl. The reaction is very sensitive, and so it is done at a very low temperature from about 273 to 278 kelvins, and this gives us an important intermediate. This is N triple bond N plus and Cl minus. This is called benzene Diazonium chloride. If you look at this part here, N triple bond N, you know that N triple bond N is one of the best leaving groups you come across. So again, this reaction also involves a good leaving group, and when this good leaving group is simply treated with a source of OH, you need not take up a stronger source like NaOH or KOH, but you may simply take up or simply perform hydrolysis. So you may use H2O and H plus, dilute acid or water, and just warm it a little, and you get OH plus N2 plus HCl. You must be wondering, and first of all, what is this called? This is phenol. So now you must be wondering what is happening here. We have been continuously trying to put a good leaving group on the ring and then replacing it with OH. The reactions in general would be called aromatic substitution, but this aromatic substitution reaction follows the kinetics of SN1 type of reaction. So here, before OH gets linked onto the benzene ring, you have the leaving group leaving the ring, and then the ring gets occupied by OH. Just remember one thing, that here a carbocation is going to get formed here. right? So ring is going to attach, ring is going to get a positive charge, and then there would be the OH group getting onto that ring, giving you phenol. So the reaction is of SN1 type, right? So now this is the third way of producing phenol. We move on to the fourth method of producing phenol. Okay, let us take up the next process, that's the cummene process. This is also an industrial process and one of the very good methods of producing phenol. The process begins with the first step, which is a Friedel-Crafts alkylation being done on benzene. So when benzene is treated with propene in presence of H3PO4 and about 523 kelvins temperature, you get CH, CH3 and CH3. This is the first step. This is what we call as isopropyl benzene or cummene. You may even give a very specific name. It is just that this is a side chain, and second carbon is directly connected to the parent chain. So we may even write this as 2-isopropyl benzene. This is also one way of calling it. So basically this is cummene. Remember, there are many times they take up reactions in which they don't give you something like this, the propene. Obviously this is the standard condition which is given in our books, but then you may even have benzene been reacted with CH3, CH2, CH2Cl and anhydrous AlCl3. What do you think should be happening here? Again, you get cummene. So this is one more way of producing cummene. The question is, why cummene and why not propyl benzene? Why not propyl benzene? Just think about the mechanism. Think about the stability of carbocation which is generated as an intermediate, and you would come to know about why isopropyl benzene gets formed here and not cummene. Why isopropyl or cummene gets formed here and not the normal propyl benzene. So just think about it. You may even discuss this with me in the class when you come. So now, what is further done to cummene? Cummene is then treated with oxygen. This is what we call as aerial oxidation, and this is done at a temperature of around 370 kelvins. And this may give us a product which is called cummene. This is what we have is cummene hydroperoxide. This is cummene hydroperoxide. This cummene hydroperoxide is subjected to undergo some rearrangement, and this is done under dilute acidic conditions. So when you use dilute H2SO4 and the temperature is less, so once again the temperature is around 323 to about 360 kelvins, and you find that this part, this bond gets connected here and this bond shifts here. So what we get is a phenol and plus we get a very important byproduct which can be easily separated from phenol. This is acetone or propane 2-on. This is a very useful byproduct, and this is what makes the process so important, because you have a very useful byproduct also getting reformed which can be effectively utilized. The next thing I'm going to talk about is I shall give you some insight about the mechanism of this process. Okay, let's understand the mechanism of this rearrangement. For this we start with cummene hydroperoxide. Now cummene hydroperoxide is first of all treated with a proton, so its protonation is done, and this protonation can give you a kind of product like this. OH2 plus, right? And so now what happens is this OH is converted into a good leaving group. This moves here, right? And there is shift or migration of phenyl ring onto that oxygen, and this would give us a very important rearranged product in which you have the benzene ring connected to oxygen, and this oxygen will have carbon CH3 and CH3, and this carbon would be plus. This positive carbon now is attacked by the medium itself, which is water. Water now attacks that carbon, and we therefore would end up in getting another intermediate. Let us find out what intermediate do we get. We get something here. This is O, and then we have C, or let me put it like this: O, C, CH3, CH3, H, and plus. Now so this is basically the intermediate, and the next thing that happens is we have H being taken by the oxygen belonging connected to the ring, and electrons going back, so this would result into one more simple intermediate. I can put this a little away, and I can have this here, O, and then H plus C, OH, and then we have CH3 and CH3. So this is something which we get upon the rearranged thing, and then we have the proton shift taking place. And now the last step would be lone pair here, and oxygen getting back the electrons, and you have phenol plus CH3 twice C double bond OH plus. This C double bond OH plus, finally this is our phenol, as you all know, which is formed, but this undergoes deprotonation, and it gives us CH3 C double bond O CH3. The other product which is also formed, we call this as propanone. So this is the entire mechanism for rearrangement which is observed in cummene's process. The next method of preparing phenols is from Grignard reagent. A normal phenyl magnesium bromide, which is a Grignard reagent, phenyl magnesium bromide, a normal phenyl magnesium bromide is subjected to ethereal solution. It is the ethereal solution of phenyl magnesium bromide is subjected to reaction with oxygen. In fact, oxygen is bubbled through ethereal solution of Grignard reagent. This gives us an intermediate, and this intermediate is like OMgBr. We call this as phenoxy magnesium bromide. This phenoxy magnesium bromide is further treated with H plus in water. Let me just put this a little more proper. And this gives us the corresponding phenol. And apart from that, we have some other byproduct which is like magnesium bromide hydroxide. So MgOH and Br. So this is one more reaction which produces phenol. A simple way, you take a Grignard solution of phenyl magnesium bromide and put take it in ether and then just pass oxygen gas through it, and you end up in getting phenoxy magnesium bromide. And when you acidify this solution in water, then you get the corresponding phenol. So this is again a simple way of producing phenol. Okay, the next method of producing phenol is by decarboxylation of salicylic acid. You know, the salicylic acid has one OH group and one COOH group. 2-hydroxybenzoic acid, it can also be called. Now this salicylic acid can be first of all treated with 2 moles of NaOH, which would convert both of these groups into the corresponding sodium salts. So this becomes O minus and Na plus, and this becomes COO minus and Na plus. A sodium carboxylate group is then subjected to your standard decarboxylation process by taking CaO and heating it at a very high temperature. This would result into loss of COO-Na, and we generally have O minus and Na plus. The entire COO-Na group is removed. Here we have to use 1 mole of NaOH once again. So this would also give, this is called, this mixture is called soda lime, and you have minus Na2 CO3, and you eventually get this sodium phenoxide. So I may write the name sodium phenoxide, and this sodium phenoxide further gets acidified and you have phenol being produced. So this is the sixth method for producing phenol. This is done by decarboxylation of salicylic acid using soda lime. So we've discussed six different ways of producing phenol. In my next lecture, I would be taking up properties of alcohol, the chemical properties of alcohol, and after which I would be taking up the physical properties of chemical properties of phenols. So basically the two lectures which follow after this, one would have chemical properties of alcohol and the second one would have the chemical properties of phenol. Thank you.